Hi, my name is Randy Looney. I'm the Quality Control Safety Manager, Engineering Manager here at American AVK. I'm also on several of the committees that write standards at AWWA. I'm the chairman of the C503 committee for wet barrel fire hydrants. I'm also the chairman for the Waterworks committee at the Manufacturer Standardization Society, and I'm also on the board of directors at the MSS. Today we're going to talk about how a hydrant works, and the simple response is, well, you turn the nut on top and water comes out. But in reality, there's quite a bit more to it than that. We put quite an effort into designing these things so that they work most efficiently when they're out in the field. And some of the considerations we have to look at when we're designing a hydrant is providing a smooth water flow path through the hydrant. We have to reduce friction losses as best we can through the hydrant. We want to make sure that we produce a hydrant that doesn't induce water hammer. And we want to make sure that when it's hit by a car that the hydrant will break off and cause a minimal amount of damage to the hydrant and to the car. So when we're looking at smooth water flow, we have to look at the interior of the hydrant. Every turn of the water path creates a certain amount of friction in the water flow. So the water has to come into the bottom of the hydrant, turn 90 degrees, rise up through the hydrant, make another 90-degree turn to come out the outlet nozzle. And each one of these turns induces a certain amount of friction. Now this is important because the more water you can put on a fire over a given time period, the faster you can put the fire out. So each one of these friction losses through the hydrant reduces the amount of water that can flow out of the hydrant and extends the amount of time it takes to put fire out. We also have to look at internal structures in the flow path. So we've got to consider the shape of the main valve, the shape of the seat ring, the stem coupler, even the lubrication chamber we have to look at the shape of. Changing diameters inside the hydrant will induce friction losses. We'll go over that in just a few minutes. And changing water velocities inside the hydrant is another consideration. Anytime you are changing the velocity of the water, you're expending energy to either speed it up or even slow it down. And the velocities are controlled by the diameters inside the hydrant. So to expand on that a little bit more, changes in the flow path diameter will speed up, in the case of a smaller diameter, speed up the water flow, or slow it down in large diameter portions of the fire hydrant. So this is just like putting your thumb over the end of a garden hose, that you're reducing the opening of the end of that garden hose and you're increasing the velocity so you can spray the water farther. This works the exact same way. There's a complicated calculation that can be made to compensate for all the differences of the various flow paths diameters that are inside a hydrant. We do a lot of testing with UL and also independent testing on our own. And when we do this, the hydrant is set up so that it's got an inlet pipe at the bottom. Let me skip a slide here. There's an inlet pipe coming in the bottom that's usually 6 inches in diameter, and it has a pressure sensor just in front of the hydrant on the pipe. We screw another pipe onto the outlet nozzle, and there's a second pressure sensor on the outlet nozzle. And when we're flowing water through the hydrant, we can look at the two different pressures from these two different sensors and determine what the friction losses are through the hydrant. However, we get a false reading because the outlet on the pumper is, let's say, for example, a 4-inch diameter, where the inlet at the base is a 6-inch diameter. Water is not compressible. So if you put 25 gallons into the bottom of the hydrant, you have to get 25 gallons out of the top end of the hydrant. And to do that, that means the velocity passing through that outlet nozzle has to increase. But when you increase it, the pressure drops. So we get an artificial pressure drop outside of the hydrant going through this outlet nozzle versus what's going through the inlet at the base of the hydrant. So we have another calculation that removes that, and the difference between those calculations tells us what the exact friction losses are through the center of this hydrant. We have actually done a lot of extensive testing with our hydrants, so we know exactly how much friction is induced by the little pins, the coupler, the main valve, every part inside the hydrant. We already know how much friction it induces into the water flow. And if you look at this, you'll see that things we have to contend with, we've got a 6-inch diameter pipe that brings the water to the hydrant. We've got a 5 1/4-inch diameter main valve, so now we're increasing the velocity of the water. We've got a 7-inch diameter lower barrel, and that has to be 7-inch diameter so you can remove the seat ring from the ground surface line. And then it comes up to the top of the hydrant where it has to go out an outlet nozzle, which can be either 2.5 all the way up to 5-inch diameter. So all of these different diameter changes change the velocity of the water, and when the water changes velocity, its pressure changes, and you're inducing friction into the flow. So all of that we have to look at when we're designing the hydrant. Another thing we have to look at in fire hydrants is preventing water hammer. And we found that water hammer is very common in the northeastern United States, eastern Canada. It's also common in mountainous regions that have significant elevation changes in their pipe system and therefore different pressures in their piping system. But even with that, we do find places in the plains and other areas here and there, not very common, where it still occurs. And water hammer is caused by a particular combination of flow and pressure. It's also caused by just closing the hydrant too fast. Water weighs a bit over 8 pounds per gallon. A 6-inch diameter pipe has about 1.5 gallons per linear foot of pipe. So every foot is carrying about 13 pounds of water. That pipe goes up the road 2 or 3 miles, and you start doing calculations when that hydrant's open and flowing. That's a tremendous amount of weight that's flowing through that pipe to the hydrant, and that's why you don't want to shut the hydrant off too fast. You've got the weight of a freight train coming into that hydrant, and if you suddenly close it, it'll form a shock wave that travels back up the pipe until it finds a weak spot, and it'll rupture the pipe. Every hydrant installation is different. The length of the pipe that actually feeds from the main to the hydrant varies a little bit. Depends on where the isolation valve is mounted. It depends on how many elbows and T's are in the piping system. So you can have a housing development where you've got maybe 30 hydrants installed and you've got 2 of them that are having a problem. That's because those 2 happen to be in that little window that have that particular combination of flow and pressure. So to prevent this from happening, AVK came up with what we call our HydroFlow main valve. When we first came out with it, I think about 1999, it was an option, and it was delivered to those hydrants in areas that we knew had problems. But since then, we've made it standard equipment, and every hydrant we produce today is equipped with a HydroFlow main valve. Now, the way it works, this is a cutaway. You can see the main valve right here, and here's a cutaway of the bronze seat ring on either side. As the valve is moving upwards towards closure, this seating area is getting closer and closer to the seat on the bronze seat ring. As it's getting closer and closer, you're reducing that opening, and as we've just discussed, the velocity of the water starts increasing through here. As velocity increases, its pressure drops. So as you're getting close to being closed but still slightly open, what you've done is you've formed a low pressure zone on the top of the main valve. At the same time, the water below the main valve is slowing down because it's got a smaller opening to get through. And as it slows down, its pressure increases. So as this valve is closing, we have a low pressure zone formed on the top and a high pressure zone formed underneath it. And that's what makes that valve jump, slam against the seat, form that shock wave that we know as a water hammer. So with the HydroFlow main valve, what we've done is we've added this little rubber rib to the side of the valve. As the main valve is moving upward, you notice the distance here between the seat ring and the main valve, it gets very, very small. So what we've done is we've created a narrowing here sooner than it normally would during the closing process. So we form that low pressure zone on top of the main valve sooner than it would normally form. The main valve can still move upward if it wants to because of the difference between the low pressure and the high pressure zones above and below it. But you see the distance here is still, it's quite a ways away. So this thing can jump, you still have water flow, and now you can safely close it without forming the water hammer event. All modern hydrants, as we know, are designed to break away when hit by a car. This is to minimize damage to the hydrant when it has to be put back in service, and also to minimize damage to the car and the car occupants. We designed the hydrant specifically with two parts that are designed to fracture during a collision. One is the traffic brake flange on the left, and the other is the stem coupler on the right. So during a collision with a car, the first component to fracture is the traffic brake flange. And it's designed to break when a force of about 6,000 pounds is applied to the side of the hydrant at a height roughly 18 inches above the ground line, which is about where the center of the pumper cap is located. The brake flange will usually fracture at the thin lip that is machined around the inside of the flange, and you can see that lip right here. We know that this flange is made out of a specific grade of ductile iron, and therefore we know what its strength and mechanical properties are, and from that we know how many pounds, what kind of loads we have to support when the hydrant's flowing, or what it has to fracture when it's hit by a car. So the thickness of this lip is very critical to be able to hold the pressures under normal operation, but yet fracture when it's hit by a car. So the thickness of that lip is machined to be about 3.3 millimeters thick, which is roughly about 1/8 of an inch. Depending on the angle of contact with the car and the car's speed, the flange will sometimes fracture at the bolt holes in the corners of the flange, either here or over here. And that's okay too. Our goal is to have this flange fracture. We don't care if it's through the lip or through the corners, so to minimize damage to the hydrant and also to the car. So after the traffic flange is broken, the hydrant will continue moving sideways with the car until the stem rod contacts the inside of the lower barrel. At this point, the stem coupler will fracture through the machine groove when a lateral force of about 1,100 pounds is applied to the hydrant. So in other words, the breakable flange and the stem coupler usually fracture in sequence. They don't always fracture at the same time. And you'll see this, especially in a parking lot where somebody just barely backed into a hydrant. They'll break the traffic flange, but maybe not break the coupler. Now, this coupler is an engineering nightmare. It has to withstand the loads imposed by water pressure and flow. It has to withstand the vertical loads imposed when a fire hydrant is closed very tightly, especially when you've got a fireman that's just finished fighting the fire and his adrenaline is still pumped up. They tend to crank them down pretty tight. Yet it must easily fracture when it's hit by a car. And we accomplish this by using a stainless steel alloy that has the exact physical and mechanical properties, and by the precise width and depth of the machine groove in the middle of the coupler. So we know that it'll fracture at the force that we want it to. The pins that hold the coupler are made of a high-strength stainless steel alloy to resist bending and deformation under high torque and vertical closing loads. The diameter of the pins and the diameter of the holes in the coupler are critical to restrict unwanted vertical movement. And we know that that unwanted vertical movement can contribute to a water hammer event. So we go to all this work designing a coupler that holds things tightly. It has precisely machine diameter pins and holes. We know it's going to break at a certain point when hit by a car. And we get a call from a customer saying his hydrant is chattering. And so we go out to the field, and this is what we find. This was a customer that had us come out. We pulled it apart, and the hydrant had been taken apart before, and somebody had lost the pin. And rather than put the correct pin back in, they just put a rusty nail in and bent it over. Please don't do this. The question is, the breakable traffic flange has a small notch along the inside of each bolt hole. What is the primary function of the notch? Here in the photo, you see we have two breakable flanges. This one is right side up. It's labeled this side up when it's attached to the fire hydrant. And this one's upside down. So this is what would be facing the ground. When this is bolted up to the bottom end of the hydrant, there's going to be a bolt with a big flat washer across here. So if a car is driving by on a day when we have icy roads and they've salted the roads, it's going to splash salt water up onto the side of the hydrant. And because that flat washer's got that hole sealed, that salt water can pool inside of this hole. And if it stays in there long enough, it could cause corrosion, which eventually would cause this flange to corrode and prematurely fracture at that corner. So the true purpose of those notches is there a water drain? Okay, Kevin has a question. After a car destroys the hydrant, if there is no gate valve connected to the 6-inch line, how does the running water get shut off? As an estimator, I've seen them without gate valves. You're going to have to go farther upstream to find a valve to turn it off. It's common practice that on that feeder line just in front of the hydrant that people should put an isolation gate valve on there so that they can shut the water off in case the hydrant is hit by a car, or in case that you have to do maintenance to the hydrant and take it apart. Now, that said, if a hydrant is hit by a car, typically you won't have water coming out of the hydrant because it is what we call a compression closed hydrant. The water pressure is going to keep that main valve pushed up against its seat, and you should not see any water coming out of it. So the isolation gate valve is there so you can actually shut the water off and work on the hydrant. But like you, I have seen them without gate valves. It's not a good idea. Okay, extensions. A lot of times we go out in the field and we see hydrants that have got extension kits added to them. And we find it very common to see that an extension barrel has been put onto the top of the lower barrel to extend the nozzle section higher up to the ground level. And the contractor or the installer has forgotten to move the breakable flange up with the nozzle section of the hydrant. In those cases, it ends up with this breakable flange far below ground, where if the hydrant is hit by a car, the breakable flange is non-functional. So it'll cause quite a bit of damage to the hydrant, the pipe system, and also to the car and maybe the car's occupants. So several years ago, AVK began supplying our extension kits with 2 5-bolt flanges. And the purpose of this is so you can remove the nozzle section from the hydrant lower barrel, attach the lower barrel, attach the extension barrel to the lower barrel using a 5-bolt flange on the top of the lower barrel and a 5-bolt flange on the bottom of your extension barrel. That way, that 4-bolt breakable flange has to move upward with the 4-bolt nozzle section. That way it's still above ground or at grade line, and it remains functional as a traffic breakable device. Now, last question, how does this hydrant work? And yes, that is the operating nut the guy is pointing to.
How do you make sure when you bury the hydrant and a car hits it, it does break off properly and it doesn't happen, like Kevin said, it doesn't destroy the hydrant? Is there a way to make sure that it breaks off properly?
Yes. You want to make sure that at ground level, the hydrant has basically a fulcrum, for lack of a better word, to hold the lower portion of the hydrant in place as the upper portion of the nozzle section is hit by the car so it can snap off at the traffic brake flange. The AWWA M17 manual for hydrant installations, also the AVK installation and maintenance manuals, all say or recommend that a concrete collar be put around the lower barrel of the hydrant at the ground line to provide this fulcrum point to allow the hydrant to break off at the traffic flange. We have seen hydrants installed in places where they get a lot of rain that do not have the concrete collar, and you end up with just mud supporting the hydrant. We've also seen hydrants installed in desert areas where they've got this loose sand packed around the hydrant. And if you get a vehicle moving at a very slow speed and bumps into the hydrant, rather than breaking off at the traffic flange, it'll break off below ground. So you need to have that concrete collar at the ground level to give it some support so that the traffic flange can function as it's designed to.
Great.
Is there some sort of marking that we have on the hydrant or on the that shows where it should be at ground level?
We paint a white line around the lower barrel, and this is your bury mark right here on the hydrant. This is about 2 inches below the bolts, so this still allows you to get wrenches to be able to remove this bolt and do any kind of maintenance you need to on the hydrant. But that's our bury marker right there.
Great.
Yeah, Randy, I just got one more question. I get this a lot in the field, and you know, certain people like oil lubrication, some people like grease lubrication, and they're very adamant that's the way they want their hydrants to be. Is there any advantage to either?
No, they both act as a good lubricant. It's just more customer preference. We provide both, either oil filled or grease filled. Personally, I prefer the grease filled. When you're having to do maintenance and taking the hydrant all apart, you don't lose the oil, or you don't lose the lubricant like you do with an oil when you pull the bonnet off the hydrant. All the grease will stay in the top of the bonnet. When we pick a grease or an oil for our hydrants, when we manufacture them here at the factory, one of the things we have to do when picking that grease, number one, it's got to be a food grade. Number two, it can contain no acetates, because if water does get into that lubrication chamber and mix with the lubricant that has the acetate in it, it'll form acetic acid. You'll take the hydrogen from the water and form an acid. One thing that all acids have in common is they all contain hydrogen. So you remove the hydrogen to form the acid. Water, as we know from high school chemistry, is H2O. So the hydrogen's been removed that leaves the oxygen, and oxygen is what's required to corrode iron and steel for iron oxide. So if you use a lubricant that has the acetate in it and water gets in there, you basically form the perfect corrosion environment. So when picking a grease, or lubricant, you do not want to have any acetate in the chemistry. You also want to make sure there is no silicone in the lubricant. Silicone is a great lubricant, but if you get it on the outside of the hydrant, it doesn't matter how well you clean that spot on the outside of the hydrant, you will never be able to get paint to stick to it again. The other consideration is temperature. You want to make sure that the lubricant that you pick is suitable for the temperature range where your hydrant is located. So the lubricants that we have are good down to -40 degrees and will survive up to as high as 700 degrees Fahrenheit. So if you go up into northern Canada or Alaska, the lubricant is good up there. And if you are down in Arizona or South Texas, where it gets incredibly hot in the summertime, the lubricant's good down there too.
Rick wants to know, do you have any pro tips for hydrants that do not drain back when closed due to high groundwater levels or plug drain back holes?
Typically, a lot of those areas that have that issue, they'll plug the seat rings. You can remove the seat ring out of the top of the hydrant and add an 1/8 inch NPT pipe plug into the drain holes. All of our seat rings have got threaded holes. You can go to a hardware store and get an 1/8 inch NPT plug. We recommend either stainless steel or brass. We can supply them if you don't have a hardware store around that carries them. That will prevent the groundwater from migrating inside the hydrant, but if you use the hydrant, then you're going to have some sort of a pump system to pump the water out so that it doesn't freeze for the next time you want to use the hydrant. Long-term failure rate, how long can we expect them to work in good order with minimal maintenance? If they've had minimal maintenance, they should last 75 to 100 years.
And there's another question from Greg.
Yes, other manufacturers do use a 7-inch lower barrel. That's kind of almost every manufacturer uses a 5 1/4 inch opening on the main valve. That is the diameter through the seat ring. So the seat ring is a little bit wider than that. The seat ring is actually a bit over 6 inches. And so you have to have a barrel that's big enough to be able to get that seat ring to pass through. And so almost everybody's using a barrel that's about 7 inches in diameter.
Here's one has AVK flow tested other brands.
Of course we have. I'm not going to get into a comparison here, but I can say that ours flow as well or better than any of the others on the market.
And there's Randy's information. If you have any other information, he's always, if you have any other questions, he's always available. So is Mark, our Western Region Sales Manager.